So basically, I was going to do about like one or two problems for each type of problems. Like you should kind of like know for the second exam. But feel free to interrupt me, or if there's any specific different problem that you want to go over, you can also let me know. Like it depends on how much time you kind of have throughout the class. So first, I was going to do like some examples involving inequalities. So let me start with those. And let me know, by the way, if it's too small or anything. I'm going to use maybe colors which are a bit easier to see because like this board like has been kind of destroyed by whoever was using the previous like like markers. So the main thing about inequalities that you have to remember is that when you have an inequality, in order to solve an inequality, it is more or less like solving an equality with the warning that if you multiply or divide by a negative number, that flips it. So that's what you have to be most worried about. So solving one is like solving an equality. It is like solving an equality. But, right, like there's a but here because that's what you have to be careful about. But if you multiply or divide by a negative number, the inequality gets flipped. If you Okay, so let me do an example first. Oh, I also recorded it. Oh no, you can record it. Yeah, yeah, totally. But if you need the video, I'm also recording it because like a student was sick. So I thought, just record it. Okay, it's probably going to be better quality on my Zoom. Yeah, you can also record, of course. Yes. Okay, so actually, let me start. Okay, let me write this one. Okay, let's say you were trying to solve this inequality. Actually, let me write it here just in case uh, you can see more easily. Okay, so again, when you try to solve an inequality, think about it similar to solving an equality. So if this were like an equality, you would try to isolate the x. Usually that's what you're going for. Like you want the x on its own. So first you have to kind of like get rid of all the stuff does not involve x. So the first thing does not involve x is like the 5, which is being added. So you can kind of like move the 5 to the other side as a subtraction because it was positive here, so it can be moved with the opposite sign. So from plus, it changes to minus. Okay, so is that okay so far so good? Is that making sense? And then, okay, then let's simplify this first. So 2 minus 5 is minus 3 or negative 3, right? Okay. And then you can like continue. So the next step, again, let's go slowly. The next step is that there's a 4 in the denominator. So there's a 4 that's dividing the x. So you can move it to the other side as a multiplication. So again, it changes from division changes to multiplication. So you can say that this is the same as negative 3 times x less or equal to negative 3 times 4. Okay, and negative 3x, again, let's just simplify this. 3 times 4 is 12, and there's a minus here, so it's negative 12. Okay. And then for x, to isolate the x, the only thing that you have to get rid of is of this negative 3 that's multiplying it. Okay, since it's multiplying it, it goes to the other side as a division. So, but here's where you have to be careful. So let me just put first everything. But okay, the reason why I haven't written less or equal to is because of what we were I was saying a bit earlier, which is if you have a positive or if you're dividing or multiplying by a negative number, which in this case you are, then that does reverse the inequality. So this was less or equal to, and then it becomes greater or equal to. So this is where I had, this is the only step where I reversed because all the other stuff, it was involved either subtracting or adding, which is fine. You can always do those, or multiplying with a positive number, which is also fine. Is that okay? So far, so good. Making sense. Any questions up to this point? Oh, no, we do have to simplify it. There's one more step just of simplification. Because the exam is on paper, it is less crucial than, on Alex, where you do have to simplify everything, but it's still like you do want to, even just to understand for yourself what the answer is like. Okay, that's a good. So there's a minus minus, right? Minus minus cancels, and then you just get 12/3, and 12/3 is from, oh, you have a question? I was saying. Oh, it's just like it reverses the inequality. So I just meant like, because it's like the first time you're doing that with a negative number. So yeah, let me write it. Right, so the idea is that this one gets reversed because it's like the first division that it's the first time I did a division or multiplication by a negative number. And then yes, like then you simplify as we were discussing, and so you get x greater or equal to 12/3 is 4, and minus divided by minus, like they also cancel. So you get that x is greater or equal to 4. Oh, I'm learning. Okay, so okay, so far so good. Questions up to this point? We can see. I don't know if you want to take a picture before you erase, like maybe with the cell phone, if you want. I'm also recording in different way, because I guess a student was sick, but so I can send you later the recording if you need it as well. But if someone wants to take a picture before I erase, that's because I'm trying to concern myself to this like between these kind of like two lines so that it kind of is caught by the video. Not move beyond there. Um, But yeah, so like again, like with inequalities, you just have to keep an eye on the fact that if there's like a division with by a positive or negative number, then you do need to flip it. Let's see. Okay, so let me just do another of these. Um, quickly, another inequality. So let's solve 7 times 2 minus y greater than 3 times y plus 4. Okay. Then what can you do first here? Yes. Multiply, yes. Good. 7 by 2 and 7 with y as well, right? So you distribute. Good, good. So 7 times 2 is 14, right? 7 times 2 is 14. 7 times y is just 7y, but there's a minus here, so you have to remember to include it. Very good. And then you can do the same on to the other side as well. Okay. So 3 times y is, again, it's kind of like 3y. There's nothing else that you can say about it. And 3 times 4 is 12. Is that okay? Is that making sense? And then again, when you count, think about it similar to solving an equation. So you want all the stuff with y together. So you have to combine these two terms that have a y. It is easier to work with positive numbers. So I will kind of like send the minus 7y to the other side so that it becomes plus 7. Okay, so and I will move the 12 as to the other side as a minus 12. So kind of like we'll just kind of like rearrange things a little bit. So I'll do 14 minus 12. Okay, so let's put that here. And then I'll do the 3y stays on this side. And again, the minus 7y goes to turns as plus 7y on the right side. So, yes. Why it doesn't become y? Oh, it's going to become 10y. Oh, yeah. In the next, I'm just kind of doing it super baby steps so that it's kind of like easier to keep track of. Yeah, but that's good. Yeah. The next step is just to combine them. So 3 plus 7 would give you 10y, right? So this one is going to become 10y, and the other one is 14 minus 12, which is 2. So yes, like if you wanted to, you can kind of like skip that and, just kind of like don't do this intermediate step and just kind of like simplify it a little bit more. But it's just so that it's easier to kind of like keep track of everything that's going on. Um, but okay, is that making sense? And then you're almost there. It's just that you have to leave y by itself. And so there's a 10 multiplying it. And so you can like send it to divide on the other side. So 2 over 10 would be greater than y. Okay. And this one stays as it is because it was a positive number, right? So you don't have to flip the inequality. It only gets flipped with negative numbers when you multiply or divide by something negative. And then 2 divided by 10 is 1/5 because 10 is 2 over 5. And 10 is 2 times 5. So the 2's cancel. So that is like the solution to this inequality in this case. So again, like it is the same steps as a regular equation, just with that extra care about the multiplication or division by name. Okay, then this is a slightly different problem, which is about writing the numbers in scientific notation. Okay, let me erase here. So scientific notation is just like a convenient way to express certain numbers once they get like either really large, they become really large or really small. That's kind of like a useful notation to just kind of like refer to them. So here's an example which is not usually where you would use scientific notation because it's like kind of like an easy number to understand. But like for example, if you have something like 314, right, like that's a number that kind of like is kind of like understandable, But the idea is if you wanted to write this in scientific notation, you know, uh, you want to write it kind of like as a power of 10, okay? So basically, you write it kind of like as a number between 0 and 10 times a certain power of 10. So in this case, like, it would be 3.14 because I have to put a comma because that way I would get kind of like like this number 3.14 is between 0 and 10, okay? But obviously that's not 314, so you have to move the comma or the dot by 2 spots, and that's where like the 10 squared comes from, okay? Here's another one, like for example, 1050, it's again kind of like the same idea. If you wanted to write it as first you can like write it as a number between 0 and 1, okay? So again, you could write 1.050, okay? So it's literally the same number. It's just that you put like a dot somewhere, like you put like a dot in some place, so that it just like becomes between 0 and 1. And then like you have to move the dot 3 spots to recover 1050. So it would be 10 to the 3. Um, but the idea is that it can also be used in more interesting examples. So let's say, okay, now this one is a bit more complicated. So again, if you want to express this in scientific notation, you want a number which is between 0 and 10. So in this case, like in a number, like, you kind of like forget about the zeros that the number begins with, and you kind of like see it at 2.5. Okay. But again, this is not 2.5. You have to move the comma certain like or the point and the dot certain number spots. So if you put it like if you have the dot here, which is what you would have if you put 2.5, you have to move it 1, 2 positions. Okay. And so that gives you 10 to the -2. Does that make sense? Kind of like how it works. So again, like what you want is a number. All these numbers are between 0 and 10. And then you use like a power of 10 to kind of like move around the dot so that it kind of gives you the same thing that you started with. Yeah. Oh, okay, okay. The thing is like here's okay, so let me see another way to explain it. the thing is like, actually, let me say it. Let's do it in a different way. I'll cheat. I'll cheat this way. Okay. Imagine if I got started with this, right? Actually, this is maybe a better way to think about the problem. Okay. Okay. Yes, let's do it more carefully. So if I have this number, right? Let's say I multiply this by 10, right? If you just multiply this number by 10, that means that the dot moves one spot, right? Like you move this one spot and then you get 0 point, so you get 0.25. That's what happens if you multiply this by 10. This still is a number less than 10, you know. So now let's say that you have multiplied 0.025 by 10 squared, right? So if you do it by 10 squared, now, again, just to kind of like here, the dot was moved one spot. Now here, the dot was moved two spots, right? So when you move it two spots, you get 2.5, right? Well, yes, I guess I should say here between 1 and 10, because like circle speaking in scientific notation, like you want the number to start with like some, like, you don't want something like in scientific notation that starts like at 0.3 or something like that. So, okay, so if you multiply by 10 squared, you get 2.5, okay? So, yeah, that's actually a more convenient way to think about it. So think about kind of like solving this equation for 0.025. The way to solve for 0.025 is by dividing both sides of the equation by 10 squared. So that gives you 0.025 equals 2.5 over 10 squared. Okay. But when you have an exponent, something like 10 square or like something being exponentiated in the denominator, that actually can be moved to the numerator as a minus. Like you kind of like the rules of like the exponents is that you can kind of like move it to the front uh, as a minus exponent. So actually, let's do it for a more complicated case to see if this is making sense, which is kind of like the one that I originally, but I'll do it this way because I think maybe. Okay, yeah, this one is going to be interesting. So let's say that I had 0.0000045. Okay. Okay, that's why I use glasses, because I need to double check that this is fine. Okay. Let's say you wanted to write this number in scientific notation. Okay. And this is like actually how it's used in practice. Like with really small numbers or really large numbers. That's where it really is convenient. Um, so we can kind of like start similar to this example where I'll just take this number, right? And let's say that, okay, let's try to figure out what should I put here in order to get 4.5. Because if I put 4.5, I do have like a number between 1 and 10. So let's see, you said 10 to the 6? Let's check it out. Okay, good, good. So I move 1, 2, 3, 4, 5, 6. Very good. So then you have to move it 6 spots. You have to move the dot 6 spots so that it gives you 4.5. Okay? Is that making sense? So that means that this times 10 to the 6 gives you 4.5. And then you solve by dividing, like just as before. So that means that 0.00000045 is the same as 4.5 over 10 to the 6. But this can be moved to the top by flipping the exponent to become negative. Is that making sense?
Does it stay like that?
It does stay like that, yes. Yes. So it would stay, you would leave it like this. The reason for doing this is that then when you multiply numbers in scientific notation, it becomes super easy. Okay, so let me give you another number. Let's say that you wanted to multiply this number times. Let's say the number, I'll just do something not too complicated with 20,000. Okay. So if you wanted to multiply the number with 20,000, again, like what you would do first is to switch 20,000 into scientific notation. So again, you have to put a number between 1 and 10. So you can put 2 times. Okay, let's see how many you have. 1, 2, 3, 4 zeros. So So that would give you the number in scientific notation, and then to multiply them out. So what would it be? That is 0.00000045 times 20,000. Okay. When you switch each of them to scientific notation, what happens? The first one becomes 4.5 times 10 to the negative 6. Okay. And then this is times, well, I mean, the times I'm going to write them with the X, which I don't like in general, but it's kind of convenient for this type of problem. Okay. So that's what you get if you kind of like switch each of them individually to scientific notation. And then the idea is that you kind of like multiply the part, like the powers of 10 together, and you multiply the numbers together. So you can do 4, because like the multiplication, it doesn't matter in which order you do them. So you can multiply 4 times 4.5 times 2. So I'll do 4.5 times 2 times 10 to the negative 6 times 10 to the 4. Okay. And okay, the idea is that these are not too bad to multiply because there were numbers between 1 and 10. So they're not too hard to do. Like 4.5 times 2 is just like 9, actually. So this one would give you 9. And how do you multiply 2 powers of 10? You just add up the exponents, like that's the exponent rule for multiplication. So that's one of the advantages of working. I mean, that's not specific to base 10. That's like basically what happens every single time you have the same base but different exponents. But the idea is like you just add them together. Okay, and negative 6 plus 4 is negative 2. So you get 9 times 10 to the negative 2. And if, I mean, you can leave the answer that way if you, if you want to, because we're just doing it in scientific notation. But if you want to see it more like in understandable terms, it's 0.09. Which again, if you had just started with this number and 20,000, if you had tried to multiply them directly, it would have been a lot more confusing than just like, what you get if you do the multiplication in terms of the scientific notation. Let me get some questions. What's the best? Okay, let's see. Just give me a second to check that this one has like right nice numbers like. I should check this. Okay, yeah, this one is not bad. Okay, so let me just switch gears a little bit to do some factorization problems, which are also important. So let's move to that, and then I'll kind of like do some other things. So where should I erase? Okay, so first let's try to factor. Let's try to factor the following. 12. Oh, sorry, x to the 4. Okay, so the idea when you're trying to do factorization problems, the first thing you want to identify is whether there are certain terms that they're shared in common by the both expressions. So here's one way to kind of like write this down. Let's just write 12 as 2 times 6. And well, a little bit of an overkill, but I'll write x to the 4 as x times x times x times x. Not that you have to do that, but it's just kind of like showing more explicitly. And then I'll write x squared as x times x. Okay? So it's almost like a scanning where you scan what symbols are shared, right? So for example, there's a 6 that's being shared. So you factor it by writing it to the front of the expression, and there are two x's that are shared, right? There's an x shared with this x here. So I'll write them as, well, x times x is x squared. So I'll factor 6x squared. That's basically the idea. Okay. And then basically what you put after you factor 6x squared, you kind of like put inside the parentheses the leftover stuff. And that is literally what you would get. It just imagine erasing with your, with your fist, the things that I just marked. So if you erase those, that gives you a 2 leftover piece and an x. So that gives you 2x squared. Okay. And this is always a source of confusion because if we remove the 6 and the x squared, it's not that there's 0 left. It's 1 left. 1 is always multiplying everything out. So don't, if you put a 0, that wouldn't work. What you have to put is a 1. That's what's left if you factor completely. Is that okay? Is that making sense? Okay, yes. If it's factorization, yes, like if you kind of like remove everything, like so for example, if I had like an x cubed here, right? I'm going to erase it, but if I had an x cubed here, there's like a surviving x, and then you leave that x that survived, right? So you kind of like leave the survivors, but if there's no survivors, that means that one was the survivor, not 0. That's what I was trying to say. Um, okay. And then the question is whether you can break this further. The thing that is left here is quadratic. So the question is whether this can be further broken into something smaller, right? Okay, it can, but I don't know if anyone kind of remembers what you could do in this case. What do you think? Does it ring a bell? What would you do here? Well, if you multiply, then you're undoing your steps, right? Because if you do the multiplication, you kind of like get back to where you started. So it doesn't make it more simple, it kind of like just returns to what you had at the beginning. So it's not really multiplication. Well, it actually has nothing to do, it has nothing to do with what's in front, the 6x squared. It's only related to the thing inside the parentheses. So it's only like, in fact, this is like a separate problem. I mean, not a separate problem, but it has only to do, with what's in here. So how do you factor 2x squared minus 1? Okay. Well, you can try to isolate x if you were kind of like in an equation. If that were being equated to something, then you can kind of like start solving for x. But here it's not being equated to anything. So it's not quite that way how you can isolate it. So here it's more like, okay, let's think about this. Like, these are two things that are being subtracted, right? You're subtracting two things, and the x is being squared. Okay, so there is an identity called the difference of square formula, okay, which is a good excuse to mention. So what the difference of squares says, let me write it this way. What difference of squares says is that a squared minus b squared is a minus b times a plus b. That's what difference of squares says. It's one of the most important formulas that you should know. So this is when you are subtracting the squares of two things, okay? But here comes the confusing part, because you see this and you're like, okay, but where are all these squares? Like, you don't necessarily see everything like as a square. And the idea is that, okay, let me write it this way. First, 1 is the same as 1 squared, because 1 squared is 1. 1 to any power is 1. So, okay, now this looks a little bit more similar. It looks more similar to this formula because now you're square, like subtracting a square, but there's still this annoying 2. There's still this annoying 2 that doesn't look like a square. So how can you write 2 as a square of something? What is 2? What thing square gives you 2? What thing square gives you 2? Huh? The square root by definition, right? The square root by definition is whatever number squares to 2, like square root of 2. Right, good, good. Square root of 2 by definition of what it means is whatever number squares to 2. That's kind of like what square root of 2 means. Like, and now everything like looks like square. Everything looks squared now. So now it is, you can kind of like start comparing this with this formula if you just combine these two together, because you can write this as root of 2 of x squared minus 1 squared. Okay, and now the formula does look identical to the difference of squares if you think of root of 2x as a and 1 as b. I'll do another one of these just to make sure like we're this is because I see confusion. So, but if you apply the difference of square formula, the difference of square formula is super easy because it just says to compute it, you just literally remove the squares. You just remove the squares and then you put like a factor with the minus and another factor with the plus. So in this case, if you use the formula here, that would give you root of 2x minus 1 times root of 2x plus 1. Okay, and that is what, if you put that into this formula, you get root of 2x minus 1 times root of 2x plus 1, and that is the complete factorization of, that expression. Let me do one more of let's do another one of difference of squares just to make sure that this is making sense. Okay, let's do this one. This is kind of like a fun one. So let's say you wanted to factor. Let's say I wanted to factor x to the 4 minus 25. And I want to use the difference of square formula for that. Okay? So again, in the difference of square formulas, what the key in this formula is to have the difference of two squares. So you have to write everything as a square of something before applying it. So for example, let's start with 25. 25 is the square of what? Of 5, right? So 25 is 5 squared. Very good. Good. So we're on the right track. So this would be 5 squared. And then x to the 4 is the square of what? That's more confusing, but x to the 4 is the square of what? What thing square gives me x to the 4? Not one, you say one square. Not one square. One square gives you x to the 4. X squared. So x squared, if you think about x squared, x squared gives you x to the 4. It's kind of like silly, right? But it takes a while to get used to it. Perfect. And if you have it in that format, then I'll do another one in a moment so that you kind of like get it, like, kind of like absorb this. But then x squared is kind of like a, and 5 is like b in this formula now. So a is x squared and 5 is b. And once you recognize that, the formula is very easy because it's literally just remove the squares from the formula. So you make a copy with the squares removed, and you make another copy with a plus instead of a minus. So you have x squared minus 5. Again, so just imagine removing with your finger the exponents too. So you just get x squared minus 5 and then x squared plus 5. Okay. Which I'm still not done because this can still be further factored, but we're kind of like on the right track. Okay. So let's see. The second one, we kind of like are stuck here because this one is with a plus and not a minus. So this is the most you can do because we don't do not complex numbers in this class, like imaginary numbers like square root of -1 and things like that. So the second factor is completely done, but the first one is you can kind of like do something else to it because again, it's like a difference, right? It's a difference. You just have to interpret the second one number as a square of something. So what number squared gives you 5? Now there's the question. What number squared gives you 5? Well, so when we got square root of, when we with 2, right? When I asked what number squared gives you 2, the answer was square root of 2, right? So what number squared would give you 5 is a similar answer, but what should you have inside?
Maybe a fraction.
Not necessarily a fraction. It's still with the radic, with the square roots, but of what? The question is like of what? Square root of what square gives you 5? Let's see. Like, let me just kind of clarify by maybe writing like the first step. I want to put square root of something. What should go inside the square root so that when you square it, you get 5? It's almost like a circular answer. It's 5. Square root of 5 squared by definition is 5. So it looks like a trick, but what is square root of 5? By definition, whatever number has a property that when you square it gives you 5. That's kind of like how square roots work. Yeah, like the key formula for a square root is that, the square root of a number squared gives you that number. That's how square roots are supposed to work. A square root is whatever number squares to that number. And if you notice that, then this is not too bad because this is kind of like a difference of square again, right? This is kind of like A and B. So again, the difference of square formula just says erase the squares. And you put a version with a minus and another version with a plus. And that's what that accomplishes. Making sense, kind of. Okay, let's see. Let me do another one. Okay, let's see if this is making sense. Let's try this one. I think this should be fine. Let's see. Yeah, I think this is going to be okay. Okay. So again, you want to use a difference of square formula. So you want to see each of them as a square of something. Okay, so let's start with the easier one, which is maybe 16. What number square gives you 16? Four square gives you 16. Very good. Yeah. 4 square gives you 16. So you would put here 4 square. Perfect. And then the question is, what number squared would give you x to the 8? What do you think? Compared to the previous problem, which is kind of like a singularity.
X4 square.
X to the 4, yes. X to the 4 squared, very good. X to the 4 square would give you x to the 8. Very good. Because it's x to the 4 times x to the 4, so you have 4, which is 8, right? Is that okay? Is that making sense? Okay, so you have a square minus another square, so you can apply the difference of square formula, which again just says it is what you get if you erase the squares. So again, just imagine erasing the number 2 from each of them. So you put a version with the minus and another version with the plus. Okay, so that's what then what the difference of squares says. Oh, sorry. Yeah, it should have been a 4, right? Yeah, good. I'm glad you caught it. Thank you. Good catch. Perfect. Perfect. The second one, you're done because it's with pluses. So this can only be used when literally when it needs a difference of squares. So you need to see a difference in the formula. But you apply the same idea here. You want to write each of them as a square of something. Okay, so again, you can start with the easier one, which is one number squared gives you 4, right? One number squared gives you 4, which is 2, right? So 2 squared should be 4. Right, 2 squared should be 4. And then one number squared gives you x to the 4. Oh, we already had it here, right? X squared gives you x to the 4. Okay. So again, I'm going to apply the difference of squares to the pink term, to the pink stuff inside the parentheses. So what the difference of square formula says is that you erase the squares. So if you erase the squares, you get x squared minus 2. So you get a version with the minus and you get another version with the plus. Okay, and then you keep a version like this one, we're doing nothing to it. So you just rewrite it. Okay. And the first, okay, now the parenthesis in the middle, there's nothing you can do to it because it has a plus. So these two are kind of like already good to go, but the first one is still a difference, right? So the question is, the goal is to write it as a difference of squares one more time. So the first one is already a square because it's literally x squared. So we only have to rewrite 2 as a square, and the trick is with square root of 2. So you would write this as this is a little bit more tricky than what you would see in the exam, but it's just kind of good to do like a thorough example, where you kind of like see this applied many times, so you do kind of like get the idea of what's going on. So this is minus root of 2 squared. Okay, and the difference of square formula says that what you get is, again, you delete the squares from the formula, you get a version without with a minus, a version with the plus, and then the rest you just copy it as it is. Okay, let me do. This is kind of like on the harder end, honestly, because like, factorization is always a bit more tricky. Let me do slightly more simple problem, but they're still important. So just one that involves like the properties of the exponents. How to do that one? So again, the idea is that you kind of like see what it's affecting the parentheses. So for the first parenthesis, that's being affected by the exponent -1, which is a negative number. So the rule is that whenever you have a negative exponent, that is the same that you get what you would get if you put like a fraction where the thing that's being affected by the negative exponent goes to the denominator and it just raised by that same exponent, but to the 1. So I kind of like, I'll write the rule that I'm using here. So what I'm using here is that a to the negative n is 1 over a to the n. Okay. I'll just apply one rule at a time so that it's a little bit easier to kind of like see what's going on. So I apply first like the negative exponent rule. Yes.
What number is that? Y, cubed, and then what is that?
Oh, this one?
Yeah.
Oh, just the letter z.
Oh, Z.
Yeah. It has 3 variables here. This one, yeah. Okay, so yes, so that's kind of like the rule applied with the negative exponent, and then I'm going to apply the rule that if you have a product of numbers that are being exponentiated or that are being raised to some power, then you just raise each individual number to that power. So like what I'm going to apply, usually you write it as a times b to the n as a to the n, b to the n. But here, like you can have more than 2 factors. Like so, any number of factors that's being raised to some number, you just raise the individual factors to that number. So in this case, that would give you 2 to the 1, x squared to the 1, which I mean, it's not going to make a difference, but I'm just kind of like writing it out so that you see the property applied properly. Okay, z to the 1, and then you do it for the other one. So the other one would be, well, I can put I don't need to put anything here. So -3 squared, there's -3 squared, then x squared, and then y squared squared. So again, the exponent kind of like affects each factor. Uh, like here with this, you're talking about this negative exponent? I mean, I flipped it so that it went to the denominator and I turned the exponent into the positive version, right? Like you kind of like erase the minus sign. Is that what you're asking? Or no? Yeah. So whenever you have a negative number, a negative exponent is the same exponent. It becomes positive, but by flipping it, yeah. And then, the other thing that I will use is that if you have a power of a raised to some other power, that's the same that what you get if you multiply the exponents out. So so 2 to the 1 is just 2. 2 times 1 is 2, so that gives you x squared. 3 times 1 is 3, so that gives you y cubed. Z to the 1 is just z. So this is not super useful, super interesting because the exponent was 1, but in this case it's a little bit more interesting. Okay, so -3 squared is -3 times -3, so that gives you 9 because the negative signs cancel. X squared is x squared, but then y squared, 2 times 2 is 4, so that's where like the y to the 4 comes from. So only really maybe in the last one, like the property one, a useful one because the other ones they're a bit easier. Or you have a question? Okay, yeah, I'll do another problem. Let me just finish this one out. Okay, so then the next step would be that the x squared appears both at the top and the bottom, and in the numerator and denominator. I mean, because it's the same x squared, it kind of like gets removed, right? So you remember you can kind of cancel out terms if they appear in the same expression at the top and the bottom. And then there's something similar you can do with y to the 4 and y cubed, but not quite because there's an extra y at the top, right? So y to the 4 is y cubed times y, okay? So that's another property if you want to think about it as a property, which is that, let me use a different color. Let's see, where are all my colors? That if you have a to the m divided by a to the n, that's the same as a to the m minus n. Okay, so in this case, 4 minus 3, that gives you 1. So that gives you 9y times 2z. And that's the most you can simplify this up. There's nothing else you can do. Okay, let me do another example like this, just to see, like, let's do. And let me do the following. Okay, I don't want that. Okay, actually, I don't want something that big. Yeah, that's better. And then let's do 2 x to the -1 y squared. Okay, that's going to be a bit more interesting. Okay, so what will you do first?
12 x 12x3.
Well, it's not 12, it's 4 cubed. 4 cubed, but yeah, what you're saying is correct in the sense that you applied the 3 to each of the factors at the top, and you applied the 2 to each of the factors at the bottom. So that's good. So it becomes 4 cubed x cubed y, okay, let me write it like this. And I'll simplify that in a moment. So y to the negative 2 cubed. And then 2 squared x to the negative 1 squared, which again, I'll simplify in a moment, and then y squared. So let me stop here to see if this is making sense. Okay, so for a second. And then we use other property that, this can be simplified just by doing the multiplication. So negative 2 times 3 is negative 6, and negative 1 times 2 is negative 2. So let's do that as well. So negative 2 times 3 is negative 6. And then, well, okay. Oh, sorry, 4 cubed. Oh my God, I forgot about the 4 cubed. Which I'll also simplify in a moment. I mean, I guess just to simplify it a little bit now. What is 4 cubed? That's 4 times 4 times 4. 4 times 4 is 16, and 16 times 4 is 64. So if you want, you can write this as 64. And then 2 squared is 4, okay? So that will be simplified a bit further because 64 divided by 4 will be 16. So you can rewrite that in the next step. But I don't want to do all the steps at once. So x to the negative 1 squared, that's x to the negative 2. And then y squared is just y squared. Yes.
Where the, like, with the 3,
Uh-huh.
all the other ones is like regular square, but then with the y negative 2, add and stuff.
You mean that here I added, you're saying?
Yeah.
Well, yeah, I'm not adding, I'm doing 2 times 3, which is negative 6, right? But let's think about what this means. This is, what is negative, y to the negative 2 cubed is means y to the negative 2 times y to the negative 2 times y to the negative 2, right? That's what the cube means, that you're multiplying the number with itself 3 times, right?
Yeah, but then that would give you 8, no?
And well, it's negative 2 minus 2 minus 2, right? Like, okay, let me write it this way. What is y to the negative 2 is 1 over y squared, right? This is 1 over y squared, right? And this is 1 over y squared, correct? With the negative exponent property that we were talking about. Does that make sense?
Mhm.
And then how many copies of y do you have? You have 2 copies here, you have 2 copies here, and then you have 2 copies here. So overall, you have 6 copies of y, right? You have 1 over y times y, 1 over y times y, 1 over y times y. Right? So there's actually 6 y's, and that's what you get with 1. You get 1 over y to the 6. The 8, the 8 doesn't come like out in this case because you always have to count how many copies of the number you have. That's what the exponents are for. It does give you like y to the 6. Is that making sense? Like it gives you y to the 6. I think, okay, let me see. And this, by the way, becomes y to the negative 6, which is how I had written it. But let's see. I don't know, maybe it's like a thing about the negative sign making the issue. Imagine if I had written something like 2 squared cubed, right? If I,
No, I get that. I was just wondering why,
uh-huh.
when you square the other one,
Mhm.
I guess it's just that.
But
I get it. though.
but you see, like I'm always
When you put it in
multiplying.
parentheses, I get it, but it's.
Right, but you see, all that I'm trying to say is that if you notice, I'm always multiplying them, right? Because I did 2 times 3, which is negative 6, and I'm doing 1 times 2, well, or negative 1 times 2, which is negative 2. So I'm always multiplying them. I wasn't adding them, um, which I think is but right, like you wouldn't get 8 from the multiplications, with the 2 and the 3. That's all that I was trying to say. And that's why it's always useful to kind of like write it out if you're getting confused.
Yeah. Take time.
Okay, so -2 times -2 is 4. Right, but these are the, right, but, that's the thing, right? Like the exponents is not, the exponent just tells you how many times you're multiplying the number with itself. It's not that the number that's being multiplied is -2, right? Y to the -2, that doesn't mean that you're multiplying -2 times -2 or something like that, right? Like it means like, how many times you're multiplying the y with itself. Yeah. It's confused, it can be confusing. Is that okay, everyone else? So, and then maybe just to wrap this one up and we can finish for the day. Okay, 16 over 4 is 64 over 4 is 16. Okay, and then this negative x to the -2 can be moved up. So it gets moved up as x squared. And this y to the -6 can be moved down as y to the 6. So the minus exponent, again, whenever you have a negative exponent, you can move it to the other, either top. If it was at the top, you move it to the bottom with a positive exponent. And if it was at the bottom, you move it to the top with a positive exponent. So it's kind of like switches the position, like the height. And then x cubed times x squared is 3 plus 2 is 5. So you get 16x to the 5. And then y squared times y to the 6, 2 plus 6, that's 8. Oh, there you do have like a y to the 8, but like, it's a, after you do all the simplifications, like to the very 8. And that's and that is the simplification. Well, I did record it, so I'll send you the recording. I'll send you a link to the recorded video if you want to check it out, like after the class. But I would say probably, the trickiest part, I feel like maybe the factorization. So definitely check that out. But as I was saying, like on the exam, the problems on the exam are very similar to the ones we were just working with. But yeah, we can still talk about more about it throughout the week if you want to. But I think this is like a good place to end because it's almost like 8:50. So maybe let's just end here because we wouldn't have time to do another problem. But yeah, I'll send you an announcement with the